Stanford University.
Harmonic oscillator. Let's just very briefly review the harmonic oscillator because it's going to come up time and time again in what happens from here on in. As I said, harmonic oscillators are ubiquitous. They occur all over the place. Anytime you have a system which has an equilibrium state, it could be classical or it could be quantum mechanical, but classical in particular. If it has an equilibrium state, then you displace it from equilibrium. Generally speaking, it will oscillate. It may oscillate with more than one frequency. For example, a violin string can oscillate in the fundamental frequency. It can in the first harmonic, the second harmonic, and if you pluck it in odd ways, you can make some nasty noises, as I'm sure that Art knows. Done it many times. The nastiness because of multiple overtones clashing with each other. Well, that's probably not quite right, but you know what I mean. All right, but nevertheless, the oscillations of a violin string are a collection of oscillators of different frequency. But more important to us are the oscillators which comprise the oscillations of the electromagnetic field and other fields. We're going to come to that, and we're going to do a little bit of quantum electrodynamics, just a little bit. But basically, if you have radiation, for example, in a cavity or in a waveguide or something like that, then the radiation, the electric and magnetic fields oscillate with definite frequencies. Again, what would be the equilibrium configuration of the radiation field? I should start with something which has an equilibrium configuration. What is the equilibrium configuration of the electromagnetic field? The answer is no electromagnetic field. The vacuum, empty space with no electromagnetic oscillations in it. No electromagnetic oscillations, in other words, just empty space with no electric and magnetic fields, is the equilibrium position of the electric and magnetic fields, if you like. If you give the system a knock by, for example, sending in some microwaves or something, the system will start to oscillate, and like the violin string, it can oscillate in all of its various frequencies, and those oscillations are called photons, or that's not quite right. The oscillations are described or describe collections of photons, and we'll come to that, but not tonight. Okay, so harmonic oscillators are terribly important in many ways. Incidentally, sound waves are also oscillations. A sound wave moving through a crystal is, again, a collection of oscillations. You can think of it wrongly as each crystal oscillating independently of every other each atom oscillating independently of every other atom. But that's not really the way it works. Each atom exerts a force on the other atom, and so when you displace one, it gives a knock to the next one, and waves go through the crystal. The waves, again, are described by harmonic oscillators, and the quanta of the oscillations are not called photons, they're called phonons, for example. So these are things we're going to study, but to prepare ourselves for that, we studied a bit the harmonic oscillator, and I want to expand on it a bit, remind you what the rules are. We started with the harmonic oscillator with a Hamiltonian, which I wrote as p squared over twice the mass, and I set the mass equal to 1 just to make my life simple. You can go back and do it with a mass not equal to 1. I believe in our book art we do it with a general mass, or we do it with, yeah, okay, so it's done with a general mass. And then plus omega squared. That's the spring constant, but it also happens that omega is the frequency of the oscillator, x squared over 2. And we constructed creation and annihilation operators, a plus or minus, which happened to have been momentum plus I omega x. Now, notice, not finished yet, but notice if classically, if I were to take, this is plus or minus, if I were to take the two operators, a plus and a minus, and multiply them together, and then divide by 2, I would construct the Hamiltonian. All right, so we'll come back to that in a minute, but in order to be consistent with the notations that are ancient, we'll put a square root of 2 omega here. And those are the a pluses or minus. And if you work out classically or quantum mechanically the Hamiltonian in terms of a plus or minus, here's what you find. Oh, one more quantity. One more quantity is called n. N is equal to a plus, a minus. As simple as that. And the last time we proved that the spectrum of eigenvalues of n were just the integers starting at 0. We showed that a plus and minus were raising and lowering operators, which raised and lowered the eigenvalues of n. All right, so this is an operator whose eigenvalues are 1, 0, start with 0, no negative ones, 0, 1, 2, 3, dot, dot, dot. And finally, not finally, but moreover, the Hamiltonian is equal to omega. Now, I have left out h bar. I'm going to leave it out, but then I'm just going to show you where it goes. If we leave out h bar, the Hamiltonian is just omega times n. Now, where does that come from? If you multiply a plus times a minus, clearly you get something which looks like this. There's a 2 downstairs, that's this 2, and there's an omega downstairs. That's why I have to compensate it with an omega here, omega n. But quantum mechanically, there's a little correction, and the correction comes because the a plus and a minus don't commute. And that gave us an n plus 1/2. The 1/2 is called the ground state energy, or the well, if it was a field theory, we would call it the vacuum energy. If it is a simple harmonic oscillator, we call it either the 0-point energy or the ground state energy. And it's really a consequence of the uncertainty principle that you can't have both p and x simultaneously being 0. And since the Hamiltonian involves p squared plus x squared, there's no way they can cancel each other. So there's always going to be a residual bit of ground state energy there. You don't lose very much if you just cross it out and forget it, because an additive constant in the energy of a system really doesn't change its equations of motion. So you can ignore it, but it is there for some purposes. All right, what I wanted to do was to show you, is there anything else? Yeah, there's one other important point, that equation that went into showing that the a pluses and a minuses were raising and lowering operators. It was the commutation relations of the a plus and a minus. Dirac's rule, whenever you see two things, commute them. All right. Sometimes, of course, you get garbage, but the commutators are a minus with a plus just equal to 1. Had I not put the square roots of 2 omegas down there, the commutator would have been something a little messier. And so really the reason for dividing by square root of 2 omega here was to get rid of anything on the right-hand side, to divide it away. This commutation relation, together with the definition of n, tells you that n is quantized in integers, and the connection with the Hamiltonian is such that the Hamiltonian, or the energy levels, are these.
Question?
Yeah.
Last time you didn't really explain why it went down to state 0, and you said think about
Yeah. Why it stops at 0?
No, why 0 is included.
Oh, why 0 is included. Okay, we're going to do it. Yeah. Okay. what we're going to do is we're going to demonstrate explicitly what the ground state is, that there is a ground state, and we'll find the ground state by actually solving the Schrödinger equation. And we'll see that there definitely is a state with 0. So what is a wave function? A wave function in this context, let's just put parallel to this very tricky and clever operator structure here. Let's write down the wave function description of the same thing. State vectors are replaced by wave functions, which are functions of position. If we're talking about energy eigenstates, we could label the wave functions with a little n down here, indicating which integer they correspond to. The ground state, for example, will be psi 0. Well, the first excited state would be psi 1, and so forth. So state vectors become wave functions. Operators, x, the operator x becomes just multiplication by the coordinate x. I'm trying to remember to use capital letters for operators and lowercase letters for just numbers, lowercase. Okay, the momentum is replaced by minus I d by just derivative with respect to x. Again, there's an h bar in there if you want to keep track of h bars. Oh, if you do want to keep track of h bars, here's where it goes, right here. And that's the only place where you have to modify what I've done here. Yeah, I guess maybe also here we want to put an h bar downstairs here, I think. But and you can always figure out where the h bars go by using dimensional analysis. Using dimensional analysis and remembering the units of h bar will tell you uniquely where to put the h bars. Okay, so there's momentum. And let's check and see if there is a solution of the equation A minus on psi is equal to 0. In other words, is there a state? You know, I can answer your question faster without. Let me answer your question quickly without, and then come back to calculating. We know that there has to be a state which is the bottom state. We can't keep going down and down and down for the simple reason that the Hamiltonian is positive. It's p squared plus x squared, p squared plus omega squared x squared. An operator like that has no negative eigenvalues. Just as classically it's either positive or 0, quantum mechanically it also can't be negative. And so there's got to be a bottom. There's got to be a floor to the tower of energy levels. Okay, how can we have a floor? The only way we can have a floor is if the bottom state, let's call it O, let's call it ground state, is annihilated by the annihilated means that you get 0 when you hit it with A minus. If you didn't get 0, whatever you got on the right-hand side would be a state of 1 unit lower energy. There is no state with 1 unit lower energy. The only way for that to happen is for this to just give 0. Now, once we know that A minus on O gives 0, then we can look at N. So let's look at N now. What does N do when it hits the bottom state? Well, it is by definition A plus A minus on O, but we already know that A minus on O gives 0, so this is 0. It's an eigenvector of N with 0 eigenvalue. So there must be an the bottom state has to have 0 value of N. Okay. That's an abstract argument, but yeah.
So if 0 is an eigenvector, then shouldn't there be an eigenvector of 0 on the far right-hand side?
Sorry.
It's O.
Wait. This 0 here, this state, and this are two different things.
Right. That's the eigenvector.
That's the eigenvector, and it's normalized to 1. And it's not 0 in any sense. It's just that its name is 0. You know, if I called my friend Art here 0, that wouldn't mean Art wasn't here or didn't exist. It would just mean, you know, being unpleasant. I'm calling him 0.
You can still write the ket over there if you want.
Yeah, you can write 0 as a ket, but you have to understand it's not this 0.
No, but
It's just 0.
0, so 0 times is...
That answers my question.
0 times anything is 0, so you can write.
The fact is that it's a vector on the left-hand and right-hand side, so you can go ahead and put the vector in there, and it's just the 0 vector.
Thank you.
Yeah, but you must not call it this vector. Whatever name you give it, you've got to give it some, and the tradition is just not to write it as a vector, but just to call it 0. Yeah. In the abstract theory of vector spaces, you introduce a vector called 0, and it's sort of special. It's the only one that doesn't have a ket sign. But as you say, it is just another vector, a rather special one. Yeah. Okay. All right. So the bottom of the tower, the bottom of the energy spectrum has to be energy h bar omega times 1/2, with n equal to 0, big N equal to 0. Also little n. But let's see if we can see how far we can go in calculating all of the wave functions. Can we calculate the wave functions themselves? Now, you might ask, I can write a Schrödinger equation. I just use for p in the top equation, I use for t d by dx. For a time-independent Schrödinger equation, the right-hand side is just the energy eigenvalue times psi. Question, is it really true that you can only solve that equation? In fact, we could write down the equation. Let's write down the equation. Just time-independent, here it is, time-independent Schrödinger equation. It's minus d by dx squared, oh boy, ordinary derivative, minus 1/2. The 1/2 is the half in front of the Hamiltonian there. P squared is d second by dx squared, psi of x, plus the potential energy, plus omega squared x squared times psi of x. And if this is the time-independent Schrödinger equation, then what I want to do is to solve the equation that this is equal to, let's call it E for the eigenvalue for energy, times psi of x. That's the same as writing p squared plus omega squared x squared on a vector is equal to E times that vector. Okay, now, if you know anything about differential equations, you'll know this is a second-order differential equation. You can always solve it for any value of the energy here. Okay. But what will happen for most values of the energy is the wave function will not go to 0 at infinity. Even worse, it will exponentially explode and get big. It won't be normalizable. It will not have a finite probability under it. There's no way to normalize it. If you try to normalize it, it'll just be 0 because the integral under the square of the wave function will be infinite. To get rid of that infinity, you'll have to divide by it, and the wave function will just be 0 everywhere. So the rule is, one more rule, and we've talked about this last quarter or 3 quarters ago or whenever it was, is that what you mean by an honest vector here is one whose square integral, the square of, which is square integrable. Integral psi star psi equals 1. Okay. There are some exceptions to this. For a particle moving on an infinite line, sometimes we introduce momentum states and position states, which are a little weird in this way. But we would like the total probability to be finite, and certainly not exponentially exploding. So this is one additional restriction, and it's when the wave functions are restricted in this manner, when they really form an honest and good vector space, then that's when the rest of this applies here. It only applies if we're interested in the square integrable wave functions, which we are. And so the point is that when we write down the Schrödinger equation, there are certain definite values of energy which will have square integrable wave functions. Those are the true honest eigenfunctions. If the wave function blows up and goes to infinity, we just throw them away. We say they're not in the space. Okay, let's see if we can find psi naught, the ground state wave function. We could write the original Schrödinger equation for it, but we can be smarter than that. Instead of writing h on psi equals e psi, let's write a smarter equation, a simpler equation. Let's use the fact that we know that the annihilation operator, the lowering operator on the ground state, I don't need to call this psi naught, just naught, gives 0. Okay, what is A minus? A minus, I just want to get my signs right. A minus is proportional to p minus I omega x. Now, there's some factors in the denominator there, but we don't care about them because we're just going to write that this times psi of x equals 0. And numerical factors like square roots of omega, they don't matter in this equation. Just multiply through by them. And now remember what p is. P is minus I d by dx. Minus I d by dx minus I omega x times psi of x equals 0. Now we have a much simpler equation than we had before. It doesn't even have any second derivatives in it. It only has first derivatives in it. So we can try to solve it. The trick for solving an equation of motion like this, anybody know what the trick is? There's only a finite number of tricks in solving differential equations. There's a handful of tricks. What's that?
Separation of variables.
No, there's only one variable. What are you going to separate? That's it.
Wrong hand.
Right. Okay. One very standard trick for linear equations like this is to write the wave function as the exponential of something else. Now, this is just a matter of experience. I can't tell you how to guess that.
Yeah, you can guess it because when you multiply through by dx, you get x dx. So the equation comes out as a derivative over a
Right.
over a,
Right.
But it's the form of a logarithm.
Yeah. All right. So this happens to be the kind of equation that you solve. You can solve it in many ways, but one way of solving it is just to write psi of x is equal to e to some f of x, and try to figure out what f of x is. All right, so let's try it. First of all, of course, we can get rid of the i's here. I and I factor out. Furthermore, we can get rid of the minus sign, because both of them have minus signs. And now what's the derivative of psi of x? To calculate the derivative of psi of x, we simply differentiate and we find that, let's call it psi prime, which means the derivative, is equal to f prime, that's the derivative of f, times e to the f of x. To differentiate an exponential, you just differentiate the thing that in the argument of the exponential here, and multiply again by f of x, e to the f of x. Okay, that's psi prime, that's this here. And then we add to that, we want to add to that plus omega x psi of x, which means we're going to add to this plus omega x e to the f of x. Now you see what Michael was saying, that the e to the f of x factors out. We can get rid of it. And that's why the trick was done in the first place. Let's get rid of all of this here. And our equation is just df dx plus omega x equals 0. That's it. Equals 0. Df dx came from here, plus omega x. They both multiplied psi, so we got rid of psi. And that's our equation. All right, this is really easy to solve. A function whose derivative is a linear thing, what kind of function is that? A quadratic thing. So the solution is quite clearly going to be proportional to x squared. In fact, it's going to be f of x is equal to 1/2 omega x squared plus a constant. Let's put the constant in there. Let's put the constant in there. And that's all. Minus. Thank you. Minus 1/2 omega x squared. That tells us that psi of x is equal to e to the minus 1/2 omega x squared. What about the constant? Well, we can add it in, but that just puts a numerical constant in front of the exponential. Since I haven't bothered worrying too much about normalizing it, I'm not going to bother with the constant. Numerical constant out in front is there. It's got an omega, got a 1/(square root) of omega in it, but it's not terribly interesting for our purposes. This is psi naught of x. And notice that it goes to 0 very, very fast with x. E to the minus x squared. It's a Gaussian. It's a bell-shaped curve that goes to 0 as e to the minus 1/2 omega x squared, and is very, very square integrable. I mean, if we square it and integrate it, it's extremely convergent. And so we've succeeded in finding. Now we could go back and check that the original Schrödinger equation is satisfied. In other words, we could plug this wave function into the Schrödinger Hamiltonian up above and calculate what the energy eigenvalue is. But we already know what it is. It's going to be omega times 1/2. We know that from all the algebraic tricks over here. So if we stuck this function back into the into this Schrödinger equation, we would discover that E is equal to 1/2, just by putting it in, plugging it in, and doing it. So we know the ground state wave function. We have one eigenvector of the energy. We see what its physical properties are. It's concentrated near the origin. It's very smooth because a Gaussian function is very smooth. It's concentrated near the origin. It does what you might expect a ground state wave function of a harmonic oscillator to do. It just sits at the origin. It sits very close to the origin, or at least by close now I mean that it's concentrated near the origin. And yeah, it's the ground state. What about the first excited state? I'll do the first excited state for you. It's almost trivial, and then you can go home and have a lot of fun calculating the next 50 states. It's sort of mindless fun, but how do you do it? It's how you do it that's more interesting than what you get. Well, I don't know, they're both interesting. But you do it by saying, look, I know what the first excited state is abstractly. Abstractly, the first excited state is equal to A plus times the ground state. I know what the ground state is, and I know what A plus is. So let's just apply A plus to the ground state. Here's the ground state. A plus is P plus I omega x, and that will tell us what the first excited state is. All right, so in terms of wave functions, psi 1 of x is equal or proportional to P plus I omega x. Now P is minus I d by dx plus I omega x on e to the minus 1/2 omega x squared. So all we have to do now is to calculate a derivative. But you know, I already did this. We did it with the opposite sign here. We did it with a minus to get 0. If I do it with the opposite sign and get 0, that means if I do it with the sign here, I'm just going to get twice the answer that I would get. Go back. I did this operation on here and got 0. That's the way I solved the equation. All right, so if this plus this acting on this gives 0, then it must mean that this term and this term give the same thing apart from a sign. Well, once I know that, then I know that when you change the sign of the over here, instead of having them cancel, they'll just double the answer. So this is just going to be twice I omega. That's not so interesting. It's just a numerical factor. Happens to be imaginary, but who cares? But it has x times e to the minus 1/2 omega x squared. So structurally, it's different. It's not just the Gaussian function. It's the Gaussian function times x. What does that look like? That looks like this. Again, it's very small far away. The fact that there's an x here doesn't make it big far away because it's totally overwhelmed by the e to the minus x squared.
But it has to be minus. It has to be minus when x is negative.
Yeah, good. It's negative, yeah. Well, it's twice an imaginary number times omega, right? But whatever it does on one side, it has the opposite sign on the other side. It's an odd function. Odd meaning it changes sign when it goes through the origin. Right. So let's make it negative on this side. Goes down, and then comes up 0, and then goes to 0 again. It's odd, meaning to say that when you reflect it, it changes sign. It's anti-symmetric. You would say it's anti-symmetric. The probability, which is the square of this, is symmetric. But notice that the probability goes to 0 at the origin. If you're in the first excited state of the harmonic oscillator, the probability that you find the oscillator at the origin is 0. Interesting fact. That's the first excited state. It has the ground state had no nodes. A node means that the wave function is 0 somewheres. The ground state had no nodes. The first excited state has one node. Each time you act with A plus, you can just spend a little bit of time with it. You'll see how it works. Each time you act with A plus, you make a higher order polynomial in front of e to the minus omega squared. Each time you hit it with another A plus, it'll give you x squared plus another term, x cubed after a while. Each time you'll get a higher and higher order polynomial, and each time you'll add a node. So the next wave function, the second excited state, has 2 nodes. The third one has 3 nodes. And if you work out The 17th, it looks something like this. Each time you act with A plus, you wind up pushing the wave function out more. For example, the ground state was concentrated near the center. The factor of x here tended to push it out a little bit. Why does it push it out? Because x is bigger far away than it is nearby, and so it pushes it out. After you've done 17 factors, or maybe it's 24 or whatever, you'll find that the wave function is pushed out near the wings, small near the origin, oscillating, and then plop goes to 0. Either symmetric or antisymmetric. Either symmetric or antisymmetric. And as you go up, you get more and more wiggles, and the whole thing gets pushed out further and further. What do the wiggles mean? What's the implication of the wiggles? Wiggles mean momentum. Okay? What's the implication of it being far away from the origin? Potential energy. So as you keep exciting it, you create more and more potential energy by pushing the wave function out where x squared is large, but at the same time you create more and more momentum as that oscillator swings through the origin. What's happening is the oscillator is trying to do what classical physics tells you it ought to do, that the higher the energy, the more likely it is to be found far away, but it also may be found close, and if it's found close, it ought to have a high momentum. So that's why it tends to oscillate very quickly near the origin and more slowly far away. But that's the basic physics of it. I don't know if I drew it well. It should oscillate more rapidly near the center and less rapidly far away, just indicating the fact when it swings to the origin, of course, it has more momentum. Okay, that's, those are the first two wave functions. Yes?
So it seems like as n becomes very large, the correspondence principle does not hold for the simple harmonic oscillator.
Well, what would you say the correspondence principle is?
That when n becomes very large, it looks like a classical.
It does, well, and in fact, what you have to do to see the classical motion is you have to take wave packets. You have to superpose many energy levels. For example, if you take the ground state, start with the ground state. That's a nice smooth wave packet. Now, displace it. Displace it off to the side here. It's no longer the ground state. In fact, it's not even an energy eigenstate altogether. It does have an average energy. But now take the time-dependent Schrödinger equation. The time-dependent Schrödinger equation has every energy level oscillate with a different frequency. The result is that this wave function is not time-independent, and what happens, it starts to swing back and forth. It starts to swing back and forth. As it swings near the center, it gets lots and lots of wiggles, but it stays of the same general shape. It wiggles, and then it comes out this side after a while, nice and smooth again. And then it swings back and forth and back and forth. And it looks very much like a classical oscillator. And in fact, the higher the energy, the more it looks like a classical oscillator. Just because the higher the energy and the bigger the swings, the smaller the ratio of the uncertainty to the size of the swing. When the swing gets very big, it sort of dominates the spatial structure of it. Okay, that's the basic physics of the harmonic oscillator. You can work out the second level, third level. By the time you get to the fourth level, you won't want to see it anymore, but it's straightforward. Good.
Question?
Yeah.
On your drawing of the second level,
Yeah, blue.
shouldn't it go through 0 at 0? Is it going to be x squared? Is it?
No, I don't think so.
Okay, it's not-
I don't think so.
Okay.
I think there's a constant term also. Yeah, yeah, yeah. It's not just x squared times. Yeah. Right.
Question. In the Hamiltonian you wrote originally, in the upper left, there already implicitly contained the normalizability in it. So
Yeah. I'll tell you where it's assumed. You want to know where it's assumed?
Pardon?
You want to know where in this over here it was assumed? Yeah. It's assumed in the fact that A plus and A minus are Hermitian conjugates of each other. If you were to take a wider class of wave functions that were not square integrable, then A plus and A minus would not be Hermitian conjugates of each other. That's where it's assumed. And I did assume that, right. So, right.
Is there a way in general of recognizing when a Hamiltonian written?
Yeah, if it's a harmonic oscillator. And here and there, sort of sporadically, and this or that, sometimes you encounter a solvable example. And when they're solvable, they can usually be solved by these kind of tricks. But they're very rare in the space of possibilities. And by some fortunate accident, the harmonic oscillator is one of them, and the hydrogen atom, or the idealized hydrogen atom, non-relativistic hydrogen atom with a point nucleus, happens to be one of the solvable examples. Okay. Now, I have in my notes two other subjects for tonight, with the idea of discussing atoms a little bit further, but more than atoms, discussing everything that there is about quantum mechanics and field theory. Two things: spin and boson-fermion, the difference between, or what bosons and fermions are. I have, well, I guess I'll go according to my notes here. I'll follow my notes. I have spin first, and then bosons and fermions. So let's talk about half spin, the spin of the electron or the spin of the proton, which happens to be half spin, which means that the spin or the angular momentum of an electron at rest it has no orbital angular momentum, it has no r cross p, all it has is spin. So spin is a kind of angular momentum that's attached to a particle. It's your choice whether you want to think of it as just an abstract concept or whether you want to think of it as a tiny little thing which is literally spinning about an axis. And when I say it has no momentum, I mean to say it has no center of mass momentum. And it's a matter of choice and taste whether you want to think of it as literally being a little spin or just an abstract property that you, mathematical property that you attach to the electron. But whatever it is angular momentum. It transforms under rotation. When you transform, when you rotate coordinates, the state transforms. Now, we've already been through this. We spent most of a quarter talking about the half-spin system. So I'm going to go through it quickly. You should go back and read the early parts of the previous lectures. We talked about a spin having two states, up or down. But then we said, wait a minute, if it can be up or down, it can also be left or right. But if it can be left or right, it can be in or out. And we worked out the states describing those things, the operators which described the components of the spin. And I didn't tell you, but we were talking about the angular momentum of a spinning particle, or of a half-spin particle. So let's see how we can understand that now that we've talked about angular momentum. The thing that characterizes angular momentum is, first of all, that there are three components of it. But just the fact that there are three components of it is not enough. It must be that those three components are literally associated with the x, y, and z directions of space. You could have them connected with something else, some other internal dimensions or whatever, but once you have matrices, once you discover that your system is being described by matrices, 3 of them, which have the commutation relations of angular momentum, then they are angular momentum. Actually, there's no choice about that, as long as the 3 matrices you're talking about are literally associated with an x and a y and a z direction of space. So let me write down again what the basic commutation relations of angular momentum are. Li, Lj, and let's write just Lx. Let's see. Let's take the Lz with the Lx. Lz with Lx is just equal to I times Ly. Okay. And the other 3, or the other 2, are just cyclic permutations. Okay, you may have noticed that these commutation relations are closely related to the commutation relations of the Pauli matrices. So let's write the 3 Pauli matrices and check whether this is true of the 3 Pauli matrices. Here they are. Sigma z is equal to 1, minus 1, 0, 0. Now, we've made a choice. We've made an arbitrary choice. We've decided to take sigma z to be the diagonal matrix. In other words, we are working in the representation of the z component of the spin. We've chosen to take that to be diagonal. And of course, the eigenvalues, what are the eigenvalues of this matrix? The eigenvalues of this matrix are +1 and -1, representing up and down. Okay, then there was sigma x. Sigma x was 1, 1, 0, 0. And finally, sigma y is equal to -I, 0, 0. There are ambiguities in these. You can rotate them and change them, but there's nothing important happens.
There's no minus in sigma x?
No minus in sigma x. All 3 are Hermitian. A real matrix, meaning to say if its entries are real numbers, if it's Hermitian, it's symmetric. That's this and this. If a matrix is Hermitian and imaginary, it must be antisymmetric. So that's this. Okay, let's check the commutation relations. Let's multiply sigma z by sigma x. And that's equal to 1, -1, 0, 0, 0, 1, 1, 0. This times this is 0. This times this is 1 up in here. 0. Down here, -1, 0. That's not quite sigma y, but it's almost sigma y. It would be sigma y, I think, is it I times sigma y? Or minus, it's I times sigma y. Yeah. Now, that's nice, but it's not the commutator. The commutator is this minus sigma x sigma z. That's the commutator. And that has 0, 1, 1, 0. 1, 0, 0, -1. And if you go through it, you don't get 0. What do you get? Exactly the same thing you got over here. Equals I sigma y. So we have not quite what we wanted. We have instead commutator of sigma z with sigma x is twice I sigma y. Does this mean these are not angular momentum, or does it mean that we're not talking about rotations? No. It just means we've normalized the sigma matrices incorrectly. Here's the trick. Take S and define it to be sigma over 2 for each component. For each component, take S being half the Pauli matrix. Seems a little bit odd, but nobody told us what the angular momentum was supposed to be. So let's just take it and see what we get. Then we get, let's put a 2 in here, a 2 in here, and that altogether divides by 4, right? I put a 2 here, a 2 here. I've divided the whole thing by 4. 2 divided by 4 is 1/2. So, yes, half the Pauli matrices satisfy exactly what they're supposed to satisfy. SZ with SX is equal to I SY. And likewise for the other commutation relations. So we see this little system of 2x2 matrices acting on 2 component vectors up or down are actually representing a very primitive and simple angular momentum system. It's a thing which you can think of as attached to the particle. Attached to the particle is a little spin, and the little spin is simply described by this system here. Okay? But now we can answer the question, what are the eigenvalues of, let's say, the z component of the angular momentum? Let's go to the z component of the angular momentum. The z component of the angular momentum, let's put some 2's here now that we know what we want. 1/2 minus 1/2, 1/2, 1/2, 2, 2. Notice that the eigenvalues of the z component of angular momentum are 1/2 and minus 1/2. When we were working out angular momentum, I told you, and I showed you, that there were 2 kinds of multiplets. There were the half spin multiplets. Let's put 0 over here. Sorry, there were the integer spin multiplets, where the magnetic quantum number m was 0, 1, 2, 3, -1, -2, -3, and so forth, with the central point being at 0 here being one of the possibilities. Now remember, the raising and lowering operators shift you by an integer, but that doesn't say you start at 0. It says either you start with 0 or you start at 1/2. A half minus 1/2, and then 3/2 minus 3/2, depending on the overall angular momentum. If it's spin 1/2, then there's only 1/2 and minus 1/2. And that's what we have here. We could have guessed all of this by saying, look, we seem to have the mathematical possibility of having half spin. That means there are 2 states. Once we know there are 2 states, we can say the angular momentum of this one must be plus 1/2, the z component must be plus 1/2, that one minus 1/2, and we can go and start building the structure up the way we did a year and a half ago, or a year ago, whenever it was. Was it that long ago? I don't remember. Okay. So every particle has a spin. The spin may be 0. If the spin is 0, it's just called a spin 0 particle. The Higgs boson is a spin 0 particle. The deuteron is a spin 0 particle. Yes, nuclei can be particles. They are particles. They have no angular momentum in their rest frame. On the other hand, some nuclei do have spin. But some atoms have spin. But the important thing is or what we're going to concentrate on, is the half-spin particles, the electrons, the muon, neutrinos, quarks, all the ones that really we think of as fundamental, or some of the ones we think of fundamental, have half-spin. Okay, all of this means that there are two kinds of angular momentum. Orbital angular momentum, and this is true in classical physics too. Orbital angular momentum is the angular momentum of the center of mass of a system. In the center of mass frame, if the system is spinning, then it has spin. The same is true here. And what is the total angular momentum? The total angular momentum is the sum of them. It's a vector. So it's the vector sum of the two kinds of angular momentum. And it's true here too. So I'll write down the equation, but we're not going to do very much with it. The total angular momentum is called J. Again, it's a notation. I don't know where it comes from. It's again a vector, and it's equal to the orbital angular momentum L, which is r cross p, plus the spin, plus s. I just tell you that because you'll see that all over the place when you're doing quantum mechanics, particularly in atomic physics. You'll see that the total angular momentum is called J, and it's L plus S for a particle. Any questions about spin? I don't want to do too much tonight, so we can stay with spin for a while, or we can.
I'm just wondering, how do you, like, if you're given some system with a J, how would you identify S?
Well, you're usually given something different. You're usually given the knowledge that the spin is a half, for example, and that the orbital angular momentum could be 1, 0. If the orbital angular momentum is 0, then the only angular momentum it has is the spin. If the orbital angular momentum is 1, then we need some rules for what we get if we add an angular momentum 1 to an angular momentum of a half. Question is, what do you get? And I wasn't going to go into that now. The problem of the addition of angular momentum, it's a straightforward problem, but we won't do it tonight. I'd be happy to go through it another night. But there are rules, mathematical rules, for adding angular momentum of two systems. Basically, you have two systems. You have the spin system and the orbital system, or you could just have two spins, or you could have two different orbital angular momentum systems. The net system has its own angular momentum, and there are rules, quantum mechanical rules for adding them. Let's not do it now.
Question?
Yeah.
You said we could think of this, not the orbital, but the spin as being either actually like this physical thing spinning, or we can think of it in a more theoretical way.
Or abstract way. Yeah.
What is the background for the experimental background or whatever that made them introduce this notion of spin?
Well, the first experimental background came partly from spectroscopy and partly, more importantly, from the periodic table. So that's what I want to get. I want to get to the periodic table a little bit and show you how spin comes into it. It was Pauli who realized that to understand the periodic table, the electron had to have an additional property. Okay, that brings us to the issue of fermions and bosons, which is closely connected to the Pauli exclusion principle, at least in the case of fermions. All right, let me just motivate it in terms of chemistry a little bit. It was one of the motivations. The other came from spectroscopy, but it's not as clear. It's not as obvious. If you remember, the the angular momentum squared, L squared, is equal to L times L plus 1. Is that what I want? Yeah. And if we look, when we look at the levels, the energy levels of the hydrogen atom solutions, which we didn't do, but I just told you a fact. I told you a fact that there's some extra degeneracies. Each one of these has 2L plus 1 states. But there were additional degeneracies. I'll redraw them for you. The horizontal axis is L, the vertical axis is energy. These are the energy levels of the hydrogen atom. And down at the bottom is the ground state of the hydrogen atom with the lowest energy level of it all. And it's an S wave, meaning to say it has no angular momentum, no orbital angular momentum. The solutions of the Schrödinger equation. The energy is in fact negative. You start at some negative value, minus 13 point something electron volts. But I'm just putting it here arbitrarily at 0 is somewhere up here. Okay, so that's the first level. Now, at the L equals 0, there are states with, this is the state with no nodes in the wave function. Then there's one with 1 node, 2 nodes, 3 nodes, and so forth. So there are more states here. I'm just drawing them schematically, completely schematically. Okay, there are more. In fact, they get closer and closer together as they get up here near E equals 0. But that's not too important for us. Now we go to L equals 1. And at L equals 1, there's the lowest energy state of L equals 1. Each L equals 1 state has 3 components. 2L plus 1 has 3 components. And the ground state of L equals 1 has more energy than the ground state of L equals 0. Why? Because it's got angular momentum. So of course it has some more energy. So it's going to be up a little bit higher. In fact, this whole collection of levels here is going to be raised up because of the angular momentum. And it's raised up in a rather surprising and I suppose you could say elegant. I'm not sure it's elegant. It is what it is. All right, so the first L equals 1 level occurs at the same place as the second L equals 0 level. It's degenerate with it, so it's 3 states over here. And then the pattern continues. The next 3 states are degenerate with this, and so forth. Degenerate means it has the same energy. Then you go to L equals 2. I'll use a different color. You go to L equals 2, which is over here. And what you find when you solve the equations, this is supposed to be at the same level here, is you find, again, the first L equals 2 state is higher than the first L equals 1 state, but it happens to occur exactly where the second L equals 2 state is, which is exactly where the third L equals 0 state is. It's a mouthful, but you know what I mean. You go up to here. And how many states are there? 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and so forth. And that's the pattern. All right, now you count the number of states. Now you count the number of states. 1 here at this energy level. Whoops. Yeah, 1 here. 4 here. 0 angular momentum plus angular momentum 1, 4. 9 here. 16 here. Evidently L squared levels. If you look at the way electrons fill the shells in idealized, very idealized chemical description of the periodic table, where it's up there, but you see that first of all there is hydrogen, which has 1 electron. And when you look at helium, which has 2 electrons, you find out that it's consistent with an energy which would be what you would get if you put both electrons into the ground state. Things are a bit different because instead of having Let's go to helium. This is hydrogen. Let's go now to helium. Helium has a nucleus of charge 2, Q equals 2, charge 2. So it pulls on the electrons tighter. The whole structure is rescaled, but that's not important. The charge is bigger. That pulls the electrons in closer, but the basic structure is the same. And now you look at helium. You find out, first of all, there's a helium ion. Helium ion means 1 electron instead of 2 electrons. Okay? And you study the helium ion, and the helium ion looks exactly the same as the hydrogen, with the exception that you'll have to plug in twice as much charge. That spreads the energy levels out and rescales them, but same structure. So the ion looks like exactly like and the ground state of the helium ion looks as if it's 1 electron in the ground state of the helium wave function. Then you put another electron in. Okay, what do you expect? Well, the natural expectation would be if you put another electron in, the ground state of that will be put that electron also in the lowest energy state. Why do anything else? If you want to keep the energy as low as possible, put them all into the ground state. So you try that. Second electron into the ground state wave function, and it works just fine. It gives you the right rough description of the helium. It's not quite exactly right because it's ignoring the interaction between the electrons, just pretending the electrons are just experiencing the nucleus. Let's take that as a working approximation. Ignore the interaction between the electrons. Put 2 electrons into the ground state of the helium wave function, and it works. It gives you the right energy for the helium. Well, what happens if you were to make a helium ion by putting an extra electron in instead of the ion with only 1 electron? Incidentally, there's also an ion with no electrons. It's just called a deuteron, a helium nucleus. Okay, 1 electron, 2 electron, put 3 electrons in. What's the guess? Right into the ground state. Why anything else? But no, that's not what happens. What happens is it goes in to the first excited state. So you put 2 electrons in the helium into the ground state, and the third one doesn't want to be there. It wants to get into the next excited state. Why? It could have saved energy. You could have had a lower energy state in the ground state if that electron went into the ground state. Okay, so along comes Pauli and says, I have an idea. My idea is that no 2 electrons can ever get into the same state. Something about electrons is such, I won't call it a repulsion. It's not right to call it a repulsion. It's an exclusion principle. When an electron is in a state, you can't fit another one in. Somehow the mathematics won't allow it. But wait a minute. We already said we could put 2 electrons into the helium ground state. So it's talking nonsense. The Pauli exclusion principle doesn't work. It only works somehow when you put a third one in. No, Pauli said that's not what's going on. He said really you can't put 2 electrons into the same state, but an electron has more properties than just its orbital motion. He said I'm going to make up a new property, and the new property has to be such that the electron comes with 2 values of it. 2 values of it. In that case, you can put the electron, 1 electron into the ground state, and let's call it the up electron. Remember, the electron can now have 2 properties. We're going to call them up and down. We can call them left or right, or we can call them anything we want. But let's give them the new property, which Pauli eventually realized had something to do with angular momentum, and said, if you can put 2 electrons in a state, not because you can't put 2 electrons in a state, but you can put 2 electrons into the same orbital angular momentum state if you give them opposite spin. If one of them is put in the up state and the other one is put in the down state, then I can save my crazy exclusion principle. I can save my crazy exclusion principle if I assume that the electron has one more property in addition to its motion, in addition to its orbital motion, that it has a thing which I will call a spin. Now, in fact, there were previous reasons to believe in an angular momentum like that, but they're not as transparent, and I won't try to get into them. That was his basic reasoning. Electron has another property, a two-valued property. Once he knew there was a two-valued property, he was off and going. He invented matrices to describe that two-valued property. And before you know it, he had the Pauli matrices, and he understood the whole thing. But let's go to the next atom. Let's see. We go to lithium. Lithium has 3 electrons. We would naturally expect for lithium, you do the same game. Now the nucleus has charge 3, so it's much more attractive. Charge 3. You put 2 electrons into the ground state. That were for the no electron case, the 1 electron case, the 2 electron case, lithium ions. It works perfectly well to put the electrons into the ground state. Not if there's no electrons, but if there's 1 or 2. And indeed, you find out that when you put the 3rd electron into the lithium to make it neutral, it goes into the first excited state. It goes into the first excited state, meaning the state with angular momentum 1. Okay? And that works out well. It works out, the energy levels of the lithium atom work out reasonably well that way. What about the ion of lithium? Well, you've filled up the 2 lowest energy states. You have 3 states here. You could add you could add another electron in any one of these states. Let's go back a step. Let me go back a step. Let's forget for a moment the spin, and let's talk about the atoms if there was no spin, but if there was Pauli exclusion principle. Let's try Pauli's old idea, except without the spin. What would you find? Indeed, you would find one helium. In helium, you would find 1 electron, am I saying this right? In the ground state. But then to keep the energy low, you could put the 2nd electron in any one of 4 states. In any one of 4 states. If you didn't want to violate the exclusion principle. There would be 4 distinct helium atoms. 4 distinct helium atoms depending on which state you put the next electron in. That was not right. The helium ground state was unique, did not have this peculiarity. What Pauli's idea was, no, you don't go to the 2nd state here, and there are not 4 possibilities. There's just the helium atom with 1 electron and the helium atom with 2 electrons, both in the ground state. Now you come to lithium. You put the 1st electron in. Forgetting spin, where can it go? 1st electron here. I'm getting tired as usual. What I'm trying to do is explain why there are 8 different, can you see this periodic table up there? All right. The 2nd row has 8 entries, I hope. Has 8 entries. It has 8 entries. How do we understand those 8 entries?
2 times 4. 1 extra electron. We add an electron.
Yeah. We add the first 2 electrons and put them in the ground state, and that's the, and we're finished with the ground state. Right? Then, how many more states do we have if we only occupy the first excited state? In other words, how many different ways can we make atoms? Well, we can put an electron in any one of 4 states in the first excited state, but if we're allowed to play with a spin, then there's any one of 8 any one of 8 possibilities.
2, 6.
Who's it? Am I making a mistake?
P orbitals are 6.
2p6, 1s1, 1s2.
Six. There's 2 p orbitals in each of 3 spatial directions. So there's 2 electrons in each p.
There are 4 states at the first excited level.
6 are P and the other 2 are S1.
Yeah. Okay.
Is the angular momentum 0 and the 3 angular momentum 1?
I think that's it. There's angular momentum 0 and 3 angular momentum 1.
Yeah, that's the 4. But if now you double it by the spin, it becomes 8.
Yeah, you should have a total of 8, not 2. Right, that's fine.
Okay, that's how spin was discovered. That's how spin was discovered. And the fact that it really was angular momentum, that could be checked by putting the atom in a magnetic field. If the electron's additional degree of freedom was really angular momentum, that would mean that since the electron is charged, that the electron would be behaving like a little magnet. If it was really spinning and it was charged, it would behave like a little, like a magnet, like an electromagnet, current going around in a loop. If that were the case, and you put the electron into a magnetic field, preferentially it would lie along the magnetic field or opposite to the magnetic field with 2 different energy levels. Okay? So if you took the hydrogen atom with 1 electron, and now you put it in the magnetic field, the 2 possibilities for the electron spin along the magnetic field and opposite to the magnetic field would now have 2 different energy levels. So the 2 states of the hydrogen atom, which previously had been the ground state of the hydrogen atom with an electron in it, the electron could have been pointing in one way or the other way. They had exactly the same energy in the first approximation. And now you put it in a magnetic field and you find that the energy levels are split. And they're split exactly as if the electron were a little magnet because of its angular momentum. So the fact that it had angular momentum, that could be tested by putting it in a magnetic field. The fact that it had 2 levels, that was consistent with the Pauli exclusion principle and the fact that or the assumed fact that you can't put 2 electrons into the same state. Now this was all wild guessing. It was wild guessing that you couldn't put 2 electrons in the same state. It wasn't quite so wild that it was angular momentum, because that could be tested experimentally. But the next step, which I think was it Pauli? It was the one person that it wasn't was the person that the idea is named for, Fermi. Dirac. It must have been Dirac again. It might have been Pauli. It was either Pauli or Dirac, who had the idea that there are 2 kinds of particles. Particles for which satisfied the Pauli exclusion principle, where you couldn't put 2 in the same state, and particles where you could put 2 in the same state. And not only that, it was preferential to put more than 1 in the same state. It was already known that photons for our purposes now are just particles. It was already known that a classical wave of photons was simply a collection of a large number of photons all in the same state, all in the same quantum state. So it was known that there were particles that you could put into the same state. Einstein figured them out, and again, it was named after Bose because Einstein figured it out, and it wasn't Bose, although Bose did some.
Fermi was he in the mix somewhere?
What's that?
Enrico Fermi, was he in that same group?
No, he came later, and his contribution was different. The discovery of this, what is called the statistics of particles, their boson, the boson or fermion character, was Einstein and Pauli, I believe, or it might have been Einstein, Dirac, and Pauli. I'm not sure what the actual history was, and it was not the other people, although they made major contributions. I think it was Einstein who gave Bose the credit for the discovery. Yeah.
When you talk about photons, they're independent particles, but when we talk about electrons, we associate them with a hydrogen. What happens if you have just a stream of electrons?
You can't put two of them in the same state. That's why you can't make a laser that lasers electrons. A laser creates lots of photons all in the same quantum state. You would have a pretty wild thing if you could get electrons into the same state and do the same kind of things with them, but you can't. You have a rather remarkable microscope that you could, you have electron microscopes, but this would be a rather superior electron microscope.
So the momentum, this L, it's not related to rotation around the nucleus.
It is, of course it is.
If there is no nucleus, if it's just L.
Oh, then it's just R cross P. You know, a particle moving in free space, just moving along a line, can have an angular momentum, R cross P, relative to some origin. Yeah. The angular momentum is relative to an origin. That's because R is relative to an origin. The definition of R is relative to an origin. Fixing an origin, you need to, and the whole idea of rotation is about some origin. The whole idea of rotation picks, I should have emphasized that in the beginning. Whenever you're talking about angular momentum, whenever you're talking about rotation, you're picking a special point to study it about. Now, in the case of an atom, it's natural to pick the nucleus to be the point that the point of symmetry. For a particle moving in free space, every point is a point of symmetry, rotational symmetry. So it's not, it becomes a less interesting thing. But for the atom, there's a natural center to talk about rotations about. You should have emphasized that.
Question?
Yeah.
So why are there 2 rows of 8 elements and then 2 rows of 18?
18 is twice 9.
But why are there 2?
I don't know why. At some point, the whole picture breaks down and doesn't make any sense. And pretty quickly, in fact. The picture of shells and filling shells is more than a little bit naive. It completely overlooks the interactions between the electrons. Now, by the time you have a fairly large atom, there's basically as many electrons in the inner core as there are protons at the center. So to ignore the interaction of the outer electrons with the inner electrons makes no sense at all. So, I mean, the whole thing breaks down pretty badly. And then there's a zillion rules that I don't know.
This impression that the more electrons you have, the bigger the atom gets, but actually they don't get that much bigger.
No, they don't get bigger, practically not at all. And the reason is because the more electrons, what happens is very simple. The more protons you have in the nucleus, the larger the charge. That tends to pull in the inner core of the electrons, the inner shells of the electrons. And what's left over, if you have, let's say, one valence electron, is one valence electron moving in what kind of field? The field that it's moving in is n protons and n minus 1 electrons. Right? So that one extra valence electron is basically thinks it's hydrogen, and it's no bigger than hydrogen, really. It's essentially almost the same size as hydrogen. So I think that's what you were saying, right? Atoms do not get bigger appreciably. They get very slowly bigger, but they don't get appreciably bigger as you add electrons, as you add protons and electrons at the same time.
The other interesting thing that I ran into is the with hydrogen atoms, the reason that they stay as far apart from each other is because of electrical repulsion.
Hydrogen atoms?
Hydrogen.
Oh, there's also an important component from the Pauli exclusion principle.
Well, that's what I was going to say. That's the exception. The rule is for most atoms, it's Pauli repulsion that keeps them apart.
Okay. Where are we? Yeah, so we want to talk about what bosons and fermions are, yes.
This might be too much to answer, but is the exclusion principle a separate postulate?
No, yeah, at that time, yes.
Okay.
Now it is not. Now it's part of basic special relativity together with quantum mechanics. Quantum mechanics without special relativity, it's a postulate, but the postulate can be phrased in a more elegant mathematical way, and that's what we're going to do. All right, we're going to phrase the postulate in a more elegant way. Once you introduce special relativity and you combine it with quantum mechanics, it's not a new postulate. It's a consequence of special relativity, which was Dirac's discovery. Okay, instead of talking about one particle, let's talk about two particles. Well, let's go back to classical statistical mechanics for a minute. In classical statistical mechanics, or classical mechanics of a system of particles, if all the particles are the same kind of particle, the question is, do you treat them as identical particles in this following sense? In counting the number of configurations, for example, we put particles into boxes. The boxes could be little boxes in phase space, or it could just be boxes. 4 boxes we can put particles into. Let's say we have 2 particles and they're both the same kind of particle. Right? So here's a configuration. We can put two of them both into the same box. That's clearly a unique configuration. Or I can put one particle in one box and the other particle in the other box. Is that one configuration or is it 2 configurations? If these particles have names, Harry and Sally. Harry and Sally. Yeah, if they have names, then you could put Harry here, Sally here, or you could put Harry here and Sally here, and there seem to be 2 different configurations. In counting configurations and calculating entropy and so forth, this could be, this sounds like it's a difference. Now, whether it is an important difference or not is a separate issue, but do you count these as separate configurations? You could always imagine that these particles which are identical to you have a tiny little bit of paint on them that paints their name on them, but it's such a weak little bit of paint, classical paint, not quantized paint. Classical paint, it's so faint, so terribly faint, that no experiment that you ever could do could detect the name imprinted on the particle, but you would have to say they were different particles. Harry here and Sally there would be different than Sally here and Harry there. Or you can say, no, I'm going to do statistical mechanics as if these were the same configuration, not think of the particles as labeled. Now, in fact, you get the same answers. It doesn't make any difference for classical statistical mechanics, but it's a conceptual difference. Putting a particle here and a particle here, is it or is it not the same as switching them if they're the same kind of particle? So that's a classical version of the notion of identical particles. And in classical statistical mechanics, we usually assume that these are the same configurations. Harry, Sally, Sally, Harry, they're the same configurations, and that's the way we do our counting. How many configurations are there for a large number of particles? Well, typically you get some n factorial different ways of relabeling the particles, and that goes into statistical mechanics. If you've taken statistical mechanics course, you know that in partition functions, there are these 1 over n factorials in them. And it's simply keeping track of the fact that if you interchange two particles, it's the same configuration. That's an assumption you make. In quantum mechanics, you don't have the luxury of doing one or the other. It is very definitely that particles are identical in the sense that they do not carry labels. 2 electrons, 1 electron here and the other electron here, is mathematically identical, and you couldn't do it otherwise, exchanging the electrons. Same with true with photons. Now, having a photon here and an electron here is not the same as having an electron here and a photon here. That's clear. That should be obvious. They have very different properties, and you can tell those two configurations apart. But interchanging and swapping around which electron is which, that's a non-transformation on the state of a system, and it also is true of photons. So let's think about that and what it tells us about the quantum state of a pair of identical particles. Let's take a pair of identical particles. This could be 2 electrons. And for the moment, let's forget spin or anything else. We just have 2 electrons in some states. Let's forget spin. How do we describe 2 particles? One particle is described by a wave function psi of x, where x is the position of the electron. What about 2 electrons? And in fact, let's go back a step. What is the psi of x? What is its meaning? It's the overlap or the inner product of an electron at x with the state of the system psi. If psi is the state vector of the electron, then its projection or its inner product onto a state localized at x is called psi of x. Suppose there were 2 electrons. How do you characterize the states of 2 electrons? Well, you characterize them by 2 positions. Position of one and position of the other. Let's call them x1 and x2. That does not stand for different directions of space now. It stands for the 2 electrons. x1 and x2, and the wave function is a function of 2 coordinates instead of 1, psi of x1 and x2. That's the wave function of a 2-particle system. It's a function of, and if you want the probability is a probability to find particle 1 at position x1, particle 2 at position x2. So we have functions of 2 variables when we have 2 particles. Now let's think of the operation of swapping the 2 particles. Taking particle 1 and replacing it by particle 2 and particle 2 by particle 1. Well, that's a transformation. That's a transformation that generally will change psi of x1 and x2. It'll change it from psi of x1, x2 to what? To psi of x2 and x1, which is not the same thing in general. A function of 2 variables does not have to be symmetric. It does not have to be such that if you interchange the 2 arguments, you get the same function back. So in general, a transformation, it's a transformation which swaps the 2 particles. Let's call that transformation, let's give it a name. It's an operator. It operates on a wave function and gives a new wave function. So let's name it. Let's call it the swap operation. Let's call it S. And here's what S does. S acts on a state with particle 1 at position x1 and particle 2 at position x2. How do I know which is particle 1? Particle 1 comes first. Particle 2 comes second. What does the swap operation do when it acts on a particle at position 1 and a second particle at position 2? It just swaps them. It gives you particle 1 at position x2 and particle 2 at position x1. It just swaps them. If the particles had little names attached to them, this would mean something. Here you would have Harry at position 1 and Sally at position 2. Here you would have Sally at position 2 and Harry at I'm not sure I said it right, but you know what I mean. Okay? You change them. You just do a little dance and switch them. Right. So this is a possible operation that you can do on the state of two particles. Here's an interesting fact. Take the operation s squared. What does s squared do? It swaps and then it swaps again. It swaps and it swaps again. What happens if you swap twice? You get back the same thing. Obviously, you get back the same thing, even if the particles have little names attached to them. If you interchange Harry and Sally and then interchange Harry and Sally again, you get back to the original naming. So what do we know about s squared? S squared must be 1 as an operator. S squared must be 1. It's a unitary operator. Why should it be a unitary operator? Because all transformations on the space of states are unitary. So here's what we know about S. S is unitary. That means it doesn't change probabilities. It doesn't change inner products. And S squared is equal to 1. What are the eigenvalues of a matrix or an operator whose square is 1? Either 1 or minus 1. The only possibility. S squared is equal to 1 means that the eigenvalues are plus 1 or minus 1. Okay, let's make a new principle. The new principle is that electrons, or that identical particles, they could be photons, they could be electrons, whatever, that for a specific kind of particle, the wave function when you interchange two particles always comes back to the same wave function. That's if s is equal to 1, or comes back to its negative if s is equal to minus 1. See what that means. Let's take the case plus 1. I think I'm beginning to fade. I think it's time to quit. I think you're probably also beginning to fade. We'll go through fermions and bosons next time. But the basic idea is classifying the wave functions of particles in terms of what happens when you switch the particles. It's a basic quantum mechanical process, or a basic quantum mechanical operation, the swapping of particles. And the notion of identical particles is basically telling you that something simple happens when you swap two particles. Either the wave function does this or it does that, and we'll do it next week.
For more, please visit us at stanford.edu.